next topic of our discussion is that of universal gravitation, which has a very remarkable history that I think some of us are familiar with. It's the great story about Copernicus and Galileo and Kepler, and then finally Isaac Newton. We're understanding the force of interaction, the fundamental force of nature that is ultimately the cause of the motion of the planets around the sun. Newton was able to discover quite a bit in that context. But I would love very much to go into the details of that history, and I certainly suggest that you read about it to get a deeper understanding of how it changed thinking at the time. But instead, I'm just going to begin with Kepler's ideas and the things that Kepler discovered. I think many of us are aware that Kepler, a brilliant mathematician, got a hold of some of the best astronomical data that was available in his time, and he was very excellent with numbers. And by observing the behavior of the motion of the planets, he was able to surmise some basic principles that are usually referred to as Kepler's three laws. So I'll begin by enumerating those laws with a little bit of discussion here. So Kepler and his three laws. The first thing that Kepler discovered, based on observation of the motion of the planets in the sky, was that as it had previously been thought that the motions would be circular, they are not in fact circular, but are elliptical. So I guess we'll just say that the first law, to be as concise as we possibly can here, is the law of ellipses. And I always spell ellipses wrong. I'll give it another try. The law of ellipses, well, the notion is this, that the motion of the planets around the sun are in fact ellipses. And I think we're familiar with the sort of oval shape of an ellipse, but of course it has a mathematical definition as well. You could say, if you wanted to say it in words, that an ellipse is a figure that has two foci. And here I've drawn the foci, and the idea is that any point on the ellipse, say this point here, sort of arbitrarily chosen, that the distance from that point to each of the foci is a constant all the way around. In some ways, or sometimes what we do to draw an ellipse is to put two pins in a piece of paper and a string, and put the pencil in the string and have it go around. Since the string is of constant length, it draws an ellipse. Another feature that the ellipse has is that if I imagine that these are two locations inside the ellipse, and I create a sound at this location, that sound bounces off the walls of the ellipse and would recombine again at the other focus. The same thing would be true of a beam of light that is shined from one point inside the ellipse. Imagine the inside of the ellipse is a mirror. Ray of light that shines from here and hits the ellipse goes to the other focus. So those are sort of ways of defining an ellipse different than the mathematical equation for an ellipse, which of course is an equation that is very much like the equation of a circle, because a circle is indeed a special case of an ellipse. If I take the two foci and I make them coincident, that is, the two foci are at the same location in space, then that ellipse is what we call a circle. And so Kepler realized that the motion of the planets could not be circles, but in fact would be ellipses. Now, that was a rather remarkable achievement, because if I was to draw the orbit of the Earth on the board for you here, you'd swear it was a circle. Of course, drawing the orbit of the Earth around the sun, I would have to draw it as an ellipse, because in fact the orbit is elliptical, and there's a certain time during the year where the Earth is closer to the sun, and a time during the year where it's further away. By the way, we are closer to the sun in the winter time. The difference in the distance to the sun does not determine the seasons. It's the tilt of the Earth that determines that, as we get more vertical rays of sun for a longer duration, heating the surface of the Earth and creating summertime conditions. But if I drew it, it would look very circular. And so detecting that lack of circular motion, not in the Earth's orbit, but in fact the orbit of Mars, which is what Kepler would have been concerned with, was a rather remarkable thing. The orbit of Mars around the sun is very, very nearly circular, but the data was precise enough that Kepler could detect that it must be an ellipse. But also, there's the motion of other objects in the sky that needs to be considered, for example, comets. Comets do come into this story, their orbits being very elliptical, and the observation of comets was something we wanted to understand. So Kepler discovered that they must be ellipses, which for him was not disconcerting, because at the time the mathematics of ellipses had just become in vogue, and I think some of you are aware of what are known as conic sections. An ellipse is one of the conic sections. If I take a cone and I intersect the cone with a plane, there are several ways that I can do that. And when I intersect a cone with a plane, I get parabola, hyperbola, ellipse, circle. All of these figures are termed the conic section. So Kepler was familiar with that, and that works. So the motion of the planets around the sun are ellipses with the sun at one focus. And so here I'll make this larger here and say that there's a star there, and at the other focus, there's nothing, empty space. And a planet goes around in an elliptical path. It's a very, very important discovery because for centuries upon centuries before that, it had been believed, of course, that the orbits were circular, and also, by the way, had been believed that the Earth was at the center of the solar system. That's more of a historical context. The second thing that Kepler observed is what we refer to as the law of areas. So I'll just write here on my list areas, and I'll explain in words what is meant by that. The law of areas, as described by Kepler, was his observation that imagine that at some point I have the planet is in this location, far away from the star, in this case, nearly as far away as it can be. And I let a certain amount of time, delta t, pass. And when I do that, coming to the other side, I travel along the orbit a little bit because the planet at this point has some speed. The speed is continuously changing, but imagine, talk about the speed on average as it goes from an initial position to the final position. What I can do is I can draw a line from the star to the planet that would be the radius or the position of the planet. If I choose the origin of the coordinates, that'd be the star. And so there's that radius and this radius. And as it moves along in the time delta t, you see there's like an area here that's swept out by the radius vector, the position vector, if you will, as it goes from the initial position to the final position. There's a certain amount of area that's swept out there. What Kepler observed was that if I look at some other time in the orbit, say over here on this near side, where it happens to be on average closer to the star, that in that same amount of time, delta t, I'm talking about exactly the same time interval on this side, delta t, the planet travels a greater distance along the arc of the orbit. It's traveling faster, and indeed that's fundamentally the observation here, that it moves faster when it's closer to the star. But I can do the same thing here and draw radius vectors, and from those radius vectors here, describe that there's some area here which is subtended by the radius at this part of the orbit. Now when I'm furthest from the star, actually the furthest point is called aphelion, just the name that we give to it, aphelion, the furthest distance from the star. And so I'm going to call this area computed here A sub A, that is the area at aphelion. And it goes, it subtends that area, the area at aphelion, in a time delta t, traveling with a speed on average that I'll call VA, the velocity at aphelion. Over here, when it's closest to the sun, this is called perihelion. Perihelion is the closest approach to the sun, and so I'll call this the area that is swept out at perihelion in a time delta t. As it moves with an average velocity, I'll call VP, the velocity at perihelion. Now what Kepler realizes from his calculations with the data that he has is that these two areas are equal one to the other. So I can write this obviously as an algebraic expression that the area at perihelion is equal to the area at aphelion. I would like to see if there's any deeper consequence of this notion, so what I want to do is actually compute these areas. I do not off the top of my head know the area of an elliptical sector. It's not an equation that any of us memorize, and I think we might have a little trouble even looking that one up. But certainly there's probably a way to compute that. There definitely is a way to compute that using calculus or whatnot, but I don't have to do anything so sophisticated. Because what I'm going to do is look at this sector at aphelion, what I've called the area at aphelion, and realize it looks very much like a triangle. All I have to do is take these two positions out here and connect them with a line, and all of a sudden that becomes a triangle. And the area of that triangle I can compute quite easily. That is, the area at aphelion is equal to 1/2 the base times the height. Well, 1/2 the base of this triangle is the distance that the planet travels in the time delta t as it passes through the aphelion point, or through the aphelion position, I guess I should say. And that's obviously going to be the velocity that it travels at aphelion multiplied by the time, delta t. That's the distance that it travels at aphelion. 1/2 the base of the triangle multiplied by the height of the triangle, which here is, on average, the radius at aphelion. So I'm going to call that RA. Haven't decided. What am I going to use? I'm going to use capital or lowercase. I often get in trouble with these things. I'm going to use lowercase. The radius at aphelion. And so that's the area of that triangle. And you might argue, well, it's not exactly the area of the triangle, because you see there's this little bit that's on the outside of it, and you've excluded that. Or you say, well, it's very, very close. It's very, very close to being the area, and so I'll say that this is done in approximation. Over here on the perihelion side, I'm going to do the same thing, and I'm going to make a triangle out of it by just connecting these two across there like that, and now I have a triangle whose area I can compute is 1/2 the base, but now it travels with a greater speed, the velocity at perihelion multiplied by delta t, which is the distance that it traveled, multiplied by the height of that triangle, which is going to be the radius at perihelion. And so I have that result as the area of that. Now, what about the circle on the other side? I think what you're saying is that maybe over here I get away with the approximation, but over here there's this huge chunk of area that I've neglected. Maybe see on this side, on the perihelion side, this approximation that I've done seems quite terrible. But here's the thing. It's only terrible because of the way that I've drawn my diagram. Imagine, if you will, that instead of choosing a time delta t that is very long, I choose a time dt, a very, very small quantity of time. And on this side, as I make the base of the triangle, that is the distance that the planet travels at aphelion, I make that smaller and smaller and smaller, you see that the approximation becomes better and better and better. The same amount of time on the other side, if I bring these two instances of observing the planet closer and closer and closer, the assumption of the triangle gets better and better and better. And that is another one of these cases we've encountered many times already in our physics, where if I make a differential argument, then approximately equal to becomes exactly equal to. And I can make the interval delta t arbitrarily small. Look what happens in my equation here. There's a dt on both sides of the equation that's exactly the same dt. Delta t, dt, very small interval of time. I divide by that interval of time and it vanishes from the equation. As does the 1/2. Here, the 1/2 disappear. And so what I have is an argument that says the velocity at perihelion multiplied by the radius at perihelion is equal to the velocity at aphelion multiplied by the radius at aphelion. Now, I've made this argument at aphelion and perihelion partly just because that's the traditional thing to do. But you might look at it and make an argument, well, if that's true at aphelion and perihelion, it's in fact true at every other point in the orbit. For example, if I choose to do it here, where I start at this, start here for the same delta t, and I go from here to here, the triangle is slightly funnier, right? Stranger looking. It's not so easy to start to make the argument. It's not the best place to start the argument. But it would still be true in that case. I make delta t really small. It's just a small triangular sector dependent on the radius. And so whereas I find that the law of areas dictates that the velocity at perihelion times the radius at perihelion is equal to the velocity at aphelion times the radius at aphelion, it's true for all points in the orbit. That is, this is equal to I guess I'm going to say, just make up some arbitrary things. It's going to be V1R1. It's also going to be V2R2. That is for every point in the orbit. It turns out to be true as well, that it's equal to V average, R average. It's true for the average velocity and the average radius as well. So this quantity, the radius, or the velocity times the radius, in the order of it written in here, appears to be a constant of the orbital motion, which is quite a spectacular thing. You know, we love it very much in our physics when we find things that do not change, when we find quantities that are conserved. Well, I imagine that something rather particular is happening here, and indeed it is. Here, my original equation with the perihelion and the aphelion, let me multiply through by the mass. That is, the mass of the orbiting body, the planet, I suppose, multiplied by the velocity at perihelion times the radius at perihelion is equal to the mass times the velocity at aphelion, the radius at aphelion. I hope you appreciate what happens. Simply multiplying both sides by the mass, which I'm perfectly allowed to do, there's nothing inappropriate about that, shows me a quantity that I am very familiar with. Angular momentum. For the motion of a planet around a star, and indeed for all orbital motion, the angular momentum is conserved. The angular momentum is conserved. Well, why would that be? Remember that the condition for the conservation of angular momentum is that external torques must be equal to zero. External torques must be equal to zero. And if the planet is the system, is there a torque exerted on the planet? Well, if the axis of rotation is the star and the angular momentum is conserved, then what we realize is that the force that acts on the planet must be directed right toward the star, right towards the axis of rotation. We know that it is the gravitational force that causes the alteration of motion, but since the angular momentum is conserved, it's an indication that that gravitational force can exert no torque on the planet. So since the force exists, but it exerts no torque, it must act through the axis of rotation. That's the only way, in our experience, that that happens. For the force to exert no torque, it must act through the axis of rotation. That is the law of areas, and Kepler, quite unaware that he had discovered the law of conservation of angular momentum. That is, he had observed the conservation of angular momentum. It wasn't until Newton had established the three laws, and those three laws had found their rotational analog, that it was realized that this was the fact. But there it is, the law of areas and the consequences of it. The third law of Kepler is the most remarkable. It's called the harmonic law. and it's the one that truly has an equation associated with it. I find this remarkable historically, and I've tried to really understand in my readings of it, research about it, tried to really understand what was going through Kepler's head when he came up with this. It's really a stroke of genius. He has fantastic amounts of observational data of the motion of the planets in the sky. And what he realizes is that if you take the time period of a planet's orbit squared and divide it by the average radius of the planet's orbit cubed, what am I going to do? I'm having a battle these days with upper or lower case and what I'm going to use. The average radius of the orbit cubed. The average radius of an orbit is a constant. I'm going to use a capital R without apology. I used a lowercase r over there. But the average radius of the orbit cubed, I'm going to use a capital R because my general philosophy of notation is that I should use a lowercase variable for lowercase for variables and uppercase for constants. I'm not going to follow that rule always, but try to use it as a guide. So he takes the time period of the orbit square divided by the average radius of the orbit cubed for all of the planets that he's aware of at the time. Of course, in his time there were planets that had not yet been discovered because even telescopic observations had not yet revealed all of the planets. But t squared over r cubed was equal to a constant. That is the same value. And of course, in physics, we enjoy constants very much. We like when things have a commonality. But the time period of the orbit squared divided by the average radius of the orbit cubed is equal to a constant is a mysterious thing. In each one of these cases, these are Kepler's 3 laws. In each one of these cases, you could ask Kepler, why does it do that? Why? What is the cause? What is the cause? And Kepler's answer would have to be, I don't know, but this is what it does. These laws, Kepler's laws, are a description of the behavior of the orbits. They're not an explanation as to why it should happen. And at the time, naturally, there was great interest in understanding why it should be so, why this behaves the way that it does. And of course, I think we all know that the solution to that came from Isaac Newton. The very same time that Isaac Newton was giving us his 3 laws, he was also thinking about universal gravitation. And so I want to go through that thought process a little bit so I can sort of cook up that equation that Newton provided us with and then immediately begin working on its consequences. So what Newton understands at the time, he begins to address the problem. He knows all of Kepler's laws. And from Kepler's laws, he can surmise a few things, and then he makes some assumptions. I'll tell you what those assumptions are. The first thing is that the force must be directed on a line from the planet to the star. Otherwise, there'd be an external torque, and the angular momentum would not be conserved. Newton would have realized that. So he knows what direction the force should be. But he also has already formulated a notion of action-reaction. That is, the motion of one object upon the other is equal and directed to opposite parts. So, if it is true that the moon, traveling along in its orbit, turns away from its otherwise straight line motion by the action of the gravitational force of the Earth pulling on the moon, then so too must the moon pull on the Earth with an equal and opposite force. So in this diagram that I've already done here, as the planet is experiencing a force directed towards the star experiences a force directed towards the planet. So why doesn't the star orbit the planet? Obviously, the reason for that, and Newton would have realized and appreciated, is that the star is fantastically massive. The star is fantastically massive. In fact, our sun is some 99% of the mass of the entire solar system is the sun. And so when the sun, our sun, or most stars, are subjected to the gravitational force of the orbiting planets, the accelerations are quite small. Although it is true that we live in an age where new extra solar planets are being discovered all the time. We've discovered hundreds and hundreds and hundreds of planets orbiting other stars. And chiefly the way we do that is that a star will wiggle under the influence of very massive planets in orbit, and we can detect that wiggle and do some very, very sensitive measurements indeed and be able to derive from that motion the motion of planets in orbit around distant stars. This is quite a remarkable achievement. But for the moment, we're going to ignore that and assume that the star is absolutely stationary. There are mathematical ways to account for the fact that the star moves as well, and I'm going to talk about those. But for the moment, I'll assume that the star is absolutely stationary, and that is the planet that moves under the influence of the force. So Newton knew that, and he knew that it was action-reaction. And so what that means for the apple in the earth, and of course we know very famously, what everyone knows, supposedly Newton sat under a tree and saw an apple fall from the tree and discovered gravity. Of course, that's not what happened. He just in the introduction to a paragraph said, just as an apple is drawn from the tree to the ground by the influence of gravity, so too is the moon drawn away from its rectilinear motion by the force of gravity. What Newton was applying at the beginning was, understand that this gravitational law that I'm about to give you is universal. That is, there's a gravitational force between you and I, and you and your notebook, and you and the Earth and the Moon, and everything in the universe mutually gravitating. So if that's the case, Newton realizes that this force of gravity that he's about to formulate must be proportional to the product of the masses. The reason is this. It's very obvious from my everyday observations that the force of gravity acting on this marker, for example, is its weight, which is its mass multiplied by the acceleration due to gravity near the surface of the Earth. If I increase the mass of the marker, then the marker becomes heavier. That is, the force of gravity is increased. So I write here that the force of gravity is proportional to the mass because if the mass is increased, then the action of the gravitational force increases. But if it's action-reaction, if I leave the marker alone and increase the mass of the Earth, that too should change the gravitational force. Increasing the mass of the Earth would increase the gravitational force. And we know now from an observed fact that the gravity on the Moon is significantly less, and the reason why is that the mass of the Moon is significantly less. So it depends on the mass of both mutually gravitating objects. Newton would have realized that. The next thing that Newton would have imagined, and did in fact imagine, is that it is extraordinarily unlikely that the gravitational influence extends everywhere in the universe uniformly. That is, the influence of the Earth that we experience here on the surface of the Earth can't possibly extend to the rest of the universe. Otherwise, the entire universe would collapse under its own gravitational interaction. All of the stars and planets and everything that ever is or ever was would gravitationally attract together. So he supposes, he's speculating here, he doesn't immediately have evidence for this, but he supposes that the gravitational strength should weaken as you go further and further away, and that the mutual gravitation of objects should weaken as they become more and more separated in space. And he had a good reason to believe this because there were other things that were known in his time that worked just this way. An example is the sound of my voice. The sound of my voice here, I, in principle, emit sound waves, which have energy associated with them. That's what vibrates your tympanic membrane and gives you the sensation of the sounds that I'm making in the lecture. In principle, it goes out spherically in all directions. If you were standing behind me right now, you could hear me talking still. And of course, there's a little, because the mouth happens to be on the front of me, there's a little bias to that. But in principle, let's imagine that it's spherical. So you hear a certain, Jules in the front row here, you hear a certain intensity of sound, a certain amount of energy per unit area, which you interpret as the loudness of my voice. But Lexi, you are twice as far away. It turns out you experience 1/4 of the sound, and the reason why is that the intensity of the sound of my voice is distributed over a spherical area. And that spherical area is 4 pi r squared. So if I double the radius of the sphere, then I quadruple its surface area, and the energy of the sound of my voice, the intensity of my voice, is spread out over the larger area. So that by the time my voice gets to Lexi, the intensity is dropped by a factor of 1/4. I go further to Brad, 3 times further away, it's 1/9. Further, 4 times further away, it's a 16th. Newton would have been aware that sound works this way. He also would have been aware that the light of a candle works this way as well, that the intensity of a light diminishes as 1 over the square of the distance. So he imagines, he makes a guess, that perhaps the gravitational interaction works the same way, that it diminishes as 1 over the square of the distance because it's a spherical phenomenon. Of course, Newton knows that the Earth is a sphere and that there's gravity everywhere pulling radially towards the center of the Earth, so he imagines that the gravitational intensity will diminish as the area over which that gravitational intensity acts increases. So he imagines that this is so. Putting these two ideas together, what Newton has to say at that point is that the force of gravity is quite possibly in some way equal to the product of the masses m1, m2 divided by the distance between them squared. That's a guess, inspired guess, but it's a guess. Naturally, Newton would seek to figure out, is this true? Is this truly the force? Well, he gives himself the method for doing that. Because if this is indeed the gravitational force, then such a force will cause an acceleration, and from the acceleration, we can determine the velocity and the position as a function of time. And so the question becomes, is the position as a function of time an ellipse? Can you work that out? So let's set about looking at the problem and what it is that Newton has to do at this point. I'll draw another ellipse for us. It's tricky to do, not such a hot-looking ellipse, but here's the sun at one focus, and then here's a planet out here, and the planet is moving along with a well-defined position vector r that describes its position in space, or a little bit to the right of its position. I'll make a little alteration here, trying to fix the error of my ways. So here it is, and this planet is moving with a velocity v. So it has a velocity. I know the radius, I know the mass, so I can, at this instant in time, as pictured, I can calculate the force. I can divide the force by the mass, and then I know the acceleration. And since the acceleration is the change in the velocity with respect to time, then I know in this instant as I've drawn it, I know in this instant what the alteration of the velocity would be. Here's Newton's problem. In the very next instant in time, the radius, as I've drawn it here, the radius will shorten, and so the force will change. The velocity vector will lengthen because it's going to speed up as it approaches the star, and it will change direction. Everything changes in every instant in time. And at the time that Isaac Newton approached this problem, no mathematical technique existed to solve this. Game over. Can't be done. Can't be done. Mathematically impossible. So Isaac Newton did exactly what any one of us would have done under the circumstances. He invented an entirely new branch of mathematics in order to solve the problem, as one does. An entirely new branch of physics that he called the method of fluxions. The method of fluxions. I kind of wish it was still the method of fluxions. You could be taking AP fluxions right now. Of course, we know historically, I'm trying not to get too much in the historical, I'm trying to cover the technical aspects, which is of the greatest interest to us. I think we can read about the history of these things, but I think we all know that Gottfried Wilhelm Leibniz was simultaneously, for mathematical reasons, inventing the same branch of mathematics. Of course, Isaac Newton, being already more famous, gets credit. And so far as we can tell historically, and they put a lot of horsepower into this, studying and researching, the two of them invented calculus simultaneously and independently. It's hard to imagine. Well, you know, if you think about it, here are two very well-educated men with a great deal of mathematical skill exposed to the same training and having the same books available, and they came to the same conclusion simultaneously. It's really not that, or maybe it is incredible, I don't know. Roughly the same time. Of course, the same time is different today because now I take my cell phone out and I say, hey, Brad, guess what I just did? And you're like, oh, I did the same thing. That's instantaneous. Here it would have been within a span of years because, you know, sailing ships and whatnot and all of those things involved. Yeah, so I don't think we'll ever know how that actually shakes out. But the fantastic thing for me is that, and the math folks, they can't really deny this, calculus was invented to solve a physics problem. Of course it was. It was done to practical purpose. You may think that practical purpose was to make you suffer. It's not. It was actually to solve this problem. And so the remarkable thing is, Isaac Newton applies the method of fluxions with the premise. With the premise, what would be the shape of the trajectory if the force has this 1 over r squared nature to it? And what he discovered was that the motion was an ellipse with mathematical purity. You don't have to force it to be an ellipse. It works out to be an ellipse. It's a remarkable thing. And as an instructor of physics, you find yourself often talking to students about this thing that Newton did. That he took the 1 over r squared law and from that was able to prove, to demonstrate, that if gravity works that way, then the motion of the planets around the sun would be ellipses. And after the holiday, and normally what happens is that you don't get to demonstrate that because it's mathematically very, very complicated. It's a very, very complicated thing. This is not a guy who sat under a tree and got hit by an apple. It's a spectacular mathematical achievement. And so after the holiday, it makes me very happy, I'll get to demonstrate to you exactly how that calculation can be done. I'm not going to do it the way Newton did it, because Newton was new to calculus at the time. He had just invented it. And so his technique is a little bit more weedy than we would like. But I've formulated my own version of it that I can probably get done in 60 minutes, and we'll see that demonstration. But for now, let's realize that what happens is, from a scientific point of view, is that that Newton makes an assumption about the nature of the gravitational force law, that he applies that gravitational force law using methods of calculus, and he's able to demonstrate that the motion of the planets around the sun would be ellipses. The experimental verification of that is that Kepler had already demonstrated that by observation, the motion of the planets are, in fact, ellipses. So Newton gets instant experimental verification of this notion. Now notice I've still written it as proportional. The thing is that Newton would have, on paper, worked things out. And when he decided to check to see, what do you think he chose for the masses? What would you choose if you were trying to do a calculation, theoretical calculation? What would you choose for the mass? 1, right? You choose 1. You're going to do it with just 1 over r squared, right? But this universal gravitational law needs to be fit to the universe. It needs to be scaled appropriately, that when I apply it to calculate the gravitational force between objects, I get right answers that are appropriate. And so another experiment has to be done. The experiment was first done by a guy named von Jolly. And von Jolly's experiment involved actually measuring the gravitational force between everyday sort of objects. There is a gravitational force between you and I right now, the gravitational force of attraction. You don't feel it, I don't feel it, because it is extraordinarily small between everyday objects. The large gravitational interaction that we see in our everyday lives is the interaction between everything around us and the Earth. But von Jolly was able to do in a clever way that actually involved using grains of sand to measure. He put two massive objects near each other and was able to cleverly contrive a way to measure the gravitational force between them. And assuming 1/r² proportion of the law, he was able to work out the constant of proportionality. The experiment was then done in a much sexier way by a guy by the name of Cavendish, using a very, very sophisticated and beautifully crafted instrument, which is now known as the Cavendish apparatus, to measure the gravitational force between objects. And in doing so, discovered that the final universal gravitational law should be written in this way. And this is obviously what's most important for you. This is why you showed up today. The universal gravitational force is the universal gravitational constant, the product of the masses m1, m2 divided by the distance between the masses squared, where g is an experimentally derived constant of the universe, so far as we know. Constant of the universe. The value of g, capital G, is the same everywhere. The value of capital G is the same everywhere in our universe. It's the universal gravitational constant. That is a cosmological assumption. How could I know that's true? I did not go to the other side of the universe and measure to see if G is the same everywhere. Another thing that I don't know is G a constant in time? Or as the universe evolves on large time scales, does G change as a function of time? I don't know that either. And a lot of our current cosmological physics is based on these assumptions of space and time. And they're really, really horrifying assumptions. It's the weakest thing I think we do in science, is make these two assumptions. That the physics that we observe today is the same physics on the other side of the universe, and that this physics is the same physics that existed in the past and will exist in the future. Well, there's nothing we can do. If you don't make those assumptions, you can't do anything. You can't take the first step. And so we have to make those assumptions. So the universal gravitational constant measured by Cavendish to be 6.67 times 10 to the minus 11th. And in finding that value, suddenly I realize a very true thing. Gravity is weak, extraordinarily weak force. 10 to the minus 11th. So here you and I are with a gravitational force of attraction between us. Let's calculate it. Your mass, my mass, maybe between us, I don't know, 10,000 kilograms, maybe, right? I'm sorry, the product of the mass. Because I got to do m1 times m2. Yeah, m1 times m2 divided by what? A meter between us squared, right? So that's 10 to the fourth. Then multiplied by 10 to the minus 11th. Gone. Virtually unmeasurable. Yeah.
Level, or is it?
Well, you see, the gravity is related to the mass. The gravity is related to the mass, so it is related to the inertia.
I mean, like the forces, like all the way down to proton electron forces. Like, is that what that's based off of? Or?
Well, I don't have to observe. Gravity does not alter microscopically. This law pertains to a gravitational force of attraction between protons, neutrons, electrons, any two objects that have mass. Yes, because matter has mass. So gravity is the interaction force associated with mass. And protons have mass, electrons have mass. However, inside of atoms and molecules and so forth, the electrodynamic interactions are fantastically stronger. So when I seek to create a kind of physics, which ultimately I will do, when I seek to create a kind of physics that governs the behavior of molecules, the gravitational interaction between molecules is irrelevant. Because, for example, let's say I'm a biologist and I'm trying to understand how DNA fragments come together and how they're unzipped and coded and all that happens. I need not consider the gravitational interaction because that force is spectacularly small, negligibly small, like calculus small, like df differentials of force small, compared to the very, very large electrical interactions between charged particles. So gravity is sort of irrelevant on the molecular scale in terms of understanding molecular dynamics.
Molecules are attracted to each other because of their proton and electrons.
Yes. No, because as I say, it's electrodynamic interaction. the gravitational interaction is so small in that context, it is irrelevant to the calculation. That's all electrodynamic. So a couple of features of this, but now I have it. I have the universal gravitational law, so I'm ready to take it out for a spin and start calculating some stuff. But before I do that, I want to talk about its features and how I apply it. And one of the things, touching sort of on the ideas that Sarah's talking about there, is, when Kepler came up with his laws and said, I don't know, this is the way it works. Kepler, why is it that way? I don't know, but this is the way they move. Now, Newton comes along and says, this is the universal gravitational force. By the way, there's a fun moment here where Newton had come back from the countryside after the plague had passed or whatever, and he ran into two of his colleagues, Hooke and a name you're probably familiar with, Halley. Edmund Halley had discovered himself a comet and was making observations of the position of the comet. In 2061, Halley's comet will revisit us. But Halley was concerned about his comet because the motion of the comet was very different from the motion of planets. The motion of the comet very different from the motion of the planets because it's extraordinarily elliptical. And so from Hooke and Halley's perspective, perhaps it had a different kind of behavior. And so Hooke and Halley ran into Newton. I always imagine it's sort of on the street or whatever, but Hooke and Halley ran into Newton, and they came up to Newton, and they said, look, there's this problem with the way the comet moves, and we're going to figure it out, and it's going to be awesome, and this is what we're working on right now is the motion of this comet. And Newton was like, yeah, I already figured that out. And they were like, the hell you say? He's like, no, I did. It works like this. And they were stunned by the brilliance of it and what he had accomplished with the gravitational interaction. They were like, Newt, you should publish. No, they didn't call him Newt. You should publish this. Newton was actually a little bit reticent to publish universal gravitation at the time. He's like, I don't know. Doesn't seem like a big deal. Yeah, it's kind of a big deal. So when he discovered it, so you meet Isaac Newton just after he's made this discovery, and you say, so Isaac, what you're saying is that there's the Earth and there's the Moon, and that the Earth exerts a gravitational force on the Moon, and indeed the Moon equal and opposite back upon the Earth, and that it is that force that causes the alteration of the Moon's orbit and causes it to go in virtually circular motion around the Earth. That's what you're telling me. Yes. How? They're not connected. If you told me that somewhere you discovered that there was a big chain connected between the Earth and the Moon, and that the Moon went around on the end of this chain in circular motion, just as I might tie a string to a rock and whirl it around my head, that would make an awful lot of sense. And by the way, Newton, I've heard that there are located behind the planets invisible angels that are beating their wings and driving them around in circular motion. Or I've also heard, and another thing that I read, that up in the heavens there are actually spheres made of crystal that are transparent, and the planets are embedded in the spheres, and as the spheres go around, you see, force by contact was a thing at the time. Like, you have to, in order to exert a force, there has to be touch. You have to make a physical connection. How then does this gravitational force act at a distance? And Newton had no idea. No idea. I can't tell you how it acts at a distance, it just does. And now in our modern picture, which I can't go into in any detail here without really, really getting off the rails, is we understand now that the presence of mass warps space-time in its vicinity, and that the gravitational interaction is actually a result of space-time curvature. And this is something that was discovered by Einstein in the general theory of relativity. So then there's Einstein, and he's all very clever, and he's come up with the general theory of relativity, and you come to Einstein and say, Bert, no, I wouldn't call him Bert. You say, well, why does it do that? Well, he doesn't know. So it's a long history of just chasing down the ideas. Why then? Yes, that's true, but now why this? There always seems to be a frontier with these things, a thing that we don't understand. So how shall I apply it? The product of the masses is easy enough, but I want to be clear about the r squared in the denominator, because if you are careless in the execution of your physics, you can make big mistakes here with the r squared in the denominator. The r is always from the center of mass of one object to the center of mass of the other. Always. The reason why I have to stress that is it appears in the equation as an r, which immediately makes everyone think radius. And it's not. R is the position vector. It's not radius. And the reason why this becomes a problem is that very often when we apply universal gravitational law, that r that appears in the denominator is coincidentally a radius of something, either a radius of circular motion or the radius of a spherical planet. And so you want to be careful about that in application. If you ever get disoriented as to what number should go there in the law, it is always center of mass to center of mass for the purpose of calculation. So now that I have a universal gravitational law, I'm going to take it out for a spin and see what I can do. Because now I can calculate forces of gravity. And you say, wait, I can already calculate forces of gravity. I've been doing that for the longest time. The force of gravity on an object is what I've been calling its weight the whole time. The weight of an object is the name for the force of gravity upon it, and I've been calculating it as m times g. M times g, the force of gravity on an object. Well, now you're telling me there's a different equation for it. Well, there is a different equation for it because I've now discovered that it's more sophisticated than I had previously thought. That's all. So what I'm going to do is take this law for gravity and put it together with my universal gravitational law. But I'm going to get a little funny with the universal gravitational law. This weight that I've used so far must be equal to the gravitational force. Now here's how I'm going to write it. The universal gravitational constant, the mass of the thing upon which the gravity acts, lowercase m, and capital M, the mass of the thing that's creating all this gravity nonsense, because the fact of the matter is we get very, very small gravitational forces unless there's a large object around to produce a large gravitational effect. The universal gravitational constant is 6 times 10 to the minus 11th. The mass of the Earth is 6 times 10 to the 24th kilograms. That's a lot of mass. That's why you have a large gravitational effect. So as a habit in my notation, I'll write a lowercase m for the mass of the thing that is orbiting or being affected, and a capital M for the large object, planet usually, or star, that's creating the gravitational effect. This is careless. This includes in it my assumption that the planet doesn't move, right? As I toss projectiles around, they move under the influence of gravity. I'm making an assumption that the acceleration of the Earth in that case is 0. It is not. If it is so small, it's unmeasurable. As I put satellites in orbit around the Earth, like the International Space Station, I'm assuming that the Earth is unaffected by the gravitational force of the space station on the Earth. That's a very good assumption. As the Earth goes in orbit around the Sun, I'm neglecting the motion of the Sun under the influence of the Earth. So I'm making that assumption, which is a very, 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 very accurate, or it leads to accurate results, right? But you should always appreciate the fact that I'm doing that. So the mass of one object, the mass of the other, divided by the distance between them squared, which for a planet like the Earth, I'm going to call r squared. And you see what I've done? I've swapped out a lowercase r for a capital R because I'm saying this is a constant quantity. In this case, a radius of a planet. Well, look what happens. I have the mass of the object being gravitated. I don't even know if that's a phrase. On both sides of the equation, it cancels. And so I've discovered a new relationship that I hadn't previously been aware of as a consequence of Newton's universal gravitational law. And that is the acceleration due to gravity is equal to g, the mass of the Earth, perhaps, divided by the radius of the Earth squared. That's because the distance between any object here in the surface of the Earth in this room, the distance between any object here and the center of mass of the Earth is the radius of the Earth. That's coincidental. The r is not radius. It's just coincidentally the radius of the Earth. You see my point? So what should happen now, now that I have this law, I should be able to calculate what is the force of gravity, or not the force of gravity, what is the acceleration of gravity near the surface of the Earth. And so I write out this calculation. The universal gravitational constant is 6.67 times 10 to the minus 11th. Here's a rare thing happening where I'm actually using numbers. And then the mass of the Earth, 6 times 10 to the 24th kilograms, divided by the radius of the Earth squared, which I just happen to know is 6.4 times 10 to the 6th meters, which then I'll squared. This would be the acceleration due to gravity on the surface of the Earth. This would be the value of g. When I calculate this, I do it in a rather easy way. That I have a number that is 10 to the minus 11th times a number that is 10 to the 24th. That makes the numerator of this 10 to the 13th, because when I multiply powers of 10, I subtract the powers. So the numerator of this calculation is 10 to the 13th. In the denominator, I have 10 to the 6th squared. That's 10 to the 12th. So I have 10 to the 13th divided by 10 to the 12th. In that case, I subtract 10 to the 13th minus, the 13 minus 12 is 1. So my answer that I get from this calculation will be times 10 to the first. I can figure that out just by observing the powers. This is a useful skill to have when doing the science of big or small numbers. Everything that we've been doing so far is sort of mesoscale, everyday scale, which is what our systems of units are designed for, everyday scale. But now things have become astronomical and numbers get quite large. What I'll calculate for, and then all I have to do to finish the calculation is 6.67 times 6 divided by 6.4 squared, which I'll discover is 0.98. And so I find that the acceleration due to gravity at the surface of the Earth should be 9.8 meters per second squared, which of course it is. 9.8 meters per second squared, which of course it is. I already knew that. I can go out in the hallway, drop things down the stairwell and measure the time to fall and figure that out. I can build a pendulum and swing it back and forth and figure that out. There's a large number of ways that I can figure out that it's 9.8 meters per second squared. Here's the beautiful thing, the remarkable thing, the lovely thing that Isaac Newton has discovered. If I know the acceleration due to gravity of the surface of the Earth, and I know the radius of the Earth, which I do by measuring shadows and stuff, I've well understood the radius of the Earth by this time, and I measure in a very clever experiment the universal gravitational force to get the proportionality of the universal gravitation right. The only thing unknown in this calculation is the mass of the Earth. This is how we know. You can't put the Earth on a pan balance. This is how we know the mass of the Earth. This is where it comes from. It's quite a remarkable thing. Not only does this ultimately get me the mass of the Earth, but the mass of all the other planets in a remarkable amount of information, which now I've run a little bit short of time, and so this is all I'm going to get to talk about today. But in our next lecture, I'll continue applying the law of universal gravitation to the solution of all kinds of problems. But here, a main takeaway of this, besides the technical aspects of it, is just the absolute remarkable genius and gift to mankind that was Isaac Newton.